the quiz for chapter 4. So maybe the doctor will bring it in the midterm. يعني it is has some possibility يعني إن شاء الله. Here we have in this question a gas of nitrogen. Okay, so we have nitrogen N2. It's filled in a piston cylinder. So start with drawing the piston cylinder. Dr. Sheikh will not bring any photos or pictures or figures. He only brings a statement. Okay. So we have a piston cylinder, and inside this piston cylinder we have nitrogen. Okay. At initial volume, so the volume of the nitrogen inside the piston cylinder is 1 meter cubed. At 300 kilopascal, so B1, 300 kilopascal. And we have the temperature is 45 degrees Celsius. Okay. An electrical heater within the device is turned on. So that is the electrical heater in the real world. Okay, they put it here. Usually we represent the electrical heater by this symbol. Okay, and it is turned on, and the electricity from 1 to 120 volt source pass through the heater. So we have a source that produces voltage. Okay, so you have positive and negative, and the current will pass through the heater. Okay, we have a current has an amount of 2 ampere. Okay, so I is equal to 2 ampere. Okay, when the current passes through the heater, it will heat the heater because the current will release heat, and this heat will be converted to the nitrogen. So it will increase the temperature of the nitrogen. Okay, so we will predict that the temperature of the nitrogen will increase. Okay, and this current will pass for a period of 10 minutes. Okay, so delta T is 10 minutes. Usually we deal with seconds, so multiply by 60 seconds. Okay, so multiply by 60 seconds over 1 minute. We'll get that the time is 600 seconds. Then a heat loss of 3000 joule occurs during the process. Okay, he means by 3000 joule from the nitrogen, because now there is heat from the electrical heater to the nitrogen, but this heat will then release through the boundary of the cylinder by conduction out of the cylinder. Okay, because we are taking the system of the closed system is the nitrogen itself. So we will care only about what cross the boundary or enter the boundary. Okay. So this Q, and it is in joule. So I wrote it as Q capital in capital letter. So Q out is 3000 joule. Okay. Also put it in kilojoule because usually we deal with kilojoule. Okay. During the process, while the nitrogen expands. Expands means when the nitrogen inside the piston cylinder, the volume of the nitrogen will increase because of the heat. When the heat released to the nitrogen, there will be more interaction between the molecules, and it will push the nitrogen will push the piston up. Okay, at constant pressure. Constant pressure, that means that B1 is equal to B2 at the next state. When we have the second state, that is the first state. The second state will be here because the piston expands. Okay, or the nitrogen expand and push the piston up. Okay, we'll have B1 equal to B2. So that what we call is quasi-equilibrium process, that we are increasing the pressure very slowly. So we are not increasing the pressure, we are moving the piston cylinder at constant pressure. So as we are not doing any increase in the pressure. Okay, that is a quasi-equilibrium process. We call it quasi-equilibrium process, as it is static, not dynamic. Okay. Determine the final temperature of the nitrogen. So we want to calculate the T2, the second temperature of the second state after the expansion. Okay. It is assumed that nitrogen has an ideal gas behavior. Usually in all the questions in the book, we assume it is ideal gas assumption for any gas. It depends on some assumptions that the pressure is low and the temperature is high. The pressure is low, approximately around 5 atmosphere to 10 atmosphere, okay, which is corresponding to 500 kilopascal to 1000 kilopascal, okay, and that the pressure that we have is less than 500 kilopascal. So usually خلاص in all the chapters, even in advanced thermodynamics, we will assume any gas that we have is ideal gas in order to use the equations of the ideal gas. BV equal to RT, BV equal to MRT, like this. Okay? And the temperature, usually, the temperature, what we mean by high temperature is above freezing. Okay? يعني, so 45 degrees, 60 degrees is high temperature for us to assume that it is an ideal gas. Okay? So I know that I will use the ideal gas equations in this question because I have this assumption. And then he said that I have the constant pressure, constant heat specific heat constant pressure CB, okay? And I have R, the gas constant. So of course, anything that usually Dr. Sharif brings, anything written in the statement, you must use it. He usually doesn't put anything that will not be used. Okay? So let's think about it. I want to calculate the final temperature, T2. And he said that I have assumptions that is ideal gas. So the first thing I will think of is to use the ideal gas law. So if I said it is state 2, right? So I will use the state 2 for the ideal gas law. So it is P2 V2 equal to MRT2, for example. Okay? I have the pressure. They say that the pressure is constant. Okay, I want to calculate the temperature. I have R, it is constant. There is nothing mentioned about the mass, okay, in the question. So I don't have the mass. And also I don't have the volume because he said it is expanding. I have the volume at the initial state, which is 1 meter cubed, but I don't know the volume at the second state. Okay, so still I have 2 unknowns, or I have 3 unknowns, so I cannot use this equation. Even if I tried the one in specific, or per mass, if I divided this equation by mass, I will get the small v equal to R T2, and still I don't have V2. Okay, so I cannot use the ideal gas equation in order to find T2 directly. So what we'll think about is that we know that that is a question from chapter 4. How to know it is a question from chapter 4? Usually there will be a mention of heat or work in the question. So you will know, oh, that is chapter 4. Or in the midterm exam, you will find, oh, I have a table that is chapter 3. I have efficiency questions that is chapter 2. So the remaining question is chapter 4. But usually we will have heat and work. Okay. If you see the questions in chapter 3, you will find also piston cylinders, you find the jet tanks, but there will no mention of heat or work in the question. But here, if there is heat or work, I will think about the chapter 4. When you have chapter 5, it will be different devices than the piston cylinder and the rigid tank. Okay? So now I know that in chapter 4, I need to make energy balance on the system, on the closed system that I have. Okay? So the energy balance, the usual equation that you usually see is Q minus W equal to delta E. I don't like this equation because they make assumption that always Qn is positive and work out is positive, and Q out is negative, and work in is negative. So sometimes it is confusing. So instead of using this equation, okay, I prefer that we make always the anything in as positive and anything out as negative. Okay, so Qn plus Wn, both of them are positive. I put also anything out as negative. So minus Q out. Let's put it in kilojoule, the usual form, minus Q out, minus work out. Okay, and delta E, if we are talking about the total energy, I have the kinetic energy, change in kinetic energy, and I have also the change in potential energy, and the change in internal energy. Okay, and usually in the questions related to piston cylinder device or rigid tanks, it is not moving, so the kinetic energy is always 0. There is no elevation, so the potential energy is always 0. So usually you will deal only with delta U. Okay, so this one is 0, and this one is 0. Okay, do I have any Qn? I have Qn from the electrical heater, but it is inside the control volume. I'm talking about Qn or Q out, W in, W out around the boundary of the system, which is the nitrogen. So I don't have Qn. Okay, so Qn is 0. Okay. Do I have work in WE, the electrical work from the electrical heater? The electrical work, usually that is the electrical work, the equation of the electrical work, it is IV times delta T, the time. Because you know from physics 2, the work or the power, you call it B, is equal to IV. Okay, and that is in kilowatt. Which is kilojoule per second. If I want to have only kilojoule, I need to multiply by delta T to get the work. Okay, here, then I will have the result in kilojoule. Okay, I have delta T, it is 600 seconds. I have the volt, I have the current, I have everything. So I can calculate WEN. Do I have Q out? I have Q out. They said it is 3000 joule, which is 3 kilojoule. Okay, so I have also Q out. This one, so I have WN and I have Q out. What about the work out? Whenever you see a piston cylinder device, you need to think about the boundary work. Okay, always you will have boundary work if the piston move expands or يعني contract or it is compressed. Okay, if there is compression or expansion. Okay, there will be a boundary work. What we mean by boundary work? This piston is moving, right? Moving either up as in this question or moving down. This boundary under the piston is a moving boundary if the gas expands or it is under compression. So because of this movement, we call it boundary work or moving boundary work. What is the role of this boundary work? It overcomes the atmospheric pressure from outside that pushes the piston, and it also يعني resist or overcome the friction between the gas itself and the boundary of the cylinder, and it also will rotate the crankshaft. If you know the the engines used in the cars, it is connected to a crankshaft, so it will also move the crankshaft. So in general, we have a boundary work in any piston cylinder device when it moves. This boundary work always will be we'll assume that it is under constant pressure. That is ideal ideal assumption, because in real life you cannot measure directly the boundary work. We need experiments. Okay, so boundary work is P dV as integration. Okay, because now the piston cylinder, we have a force exerted by the pressure of the gas itself. This force is acting on area, and the piston will move a distance, ds, for example, a differential distance. So A times ds is dv. Okay, and the force itself, okay, is the force is the force it is the force is pressure times area. Okay, and the work, any work, is force times distance, right? From physics one, force times distance. I have the force, I replace the force by BA. Okay, and D is ds. So the work here will be B A ds. I will take A ds and call it dV. Then I will make integration in order to get the work. Okay, that is the equation. Here in this case, that I will solve, the pressure is constant. So I only have to change between from the volume, the first volume to the second volume. So it will be B V2 minus V1. Okay. In the tutorial that I have in YouTube, I solved when it is isothermal, when the temperature is constant. So also watch it, because it is an important case. Okay. So I have boundary work. So let's rewrite the equation again with what we have now. I have instead of Wn, I have IV delta T, and I have Q out. Already I have the value of it. It is 3 kilojoule. And instead of the work out, I have the boundary work out, which is B V2 minus V1. Okay, and I have delta U. So why I'm doing all of this? The required from me in the question is to calculate T2. I tried the ideal gas law. I was not able to calculate T2. So what I need to do is to find another way. The only question that I thought about is the energy balance. So let's see from where I will get T2 from this equation. You know from chapter 3 that the enthalpy is equal to U plus BV. Okay, that any system or any particles or gas, liquid have internal energy. This internal energy, when it moves, it will move due to flow work, which is PV. Okay, with the because of a pressure that will move a volume of the liquid or the gas to a certain distance. Okay, so that is the enthalpy. I have here delta U and I have P and V. I can move this one, the boundary work, to the other side and say that delta H, capital, let's put it capital because they are capital here, delta H equal to delta U plus B delta V. Okay, then I will replace the boundary work and the internal energy change by delta H. So I will have I V delta T minus Q out is equal to delta H capital. Okay, H capital is H2 minus H1, and this one you will not find it in the table. So the one in the table is in kilojoule per kilogram. This one is a kilojoule. So we need to replace it by kilojoule per kilogram. So الدلتا اتش انت احنا عندنا اللي هو قانون اللي هو اتش equal to بي في بلس يو. تمام. فلما انا ده هناك هيكون it will be something like this. I will have delta u u2 minus u1, right? And I will have plus bv2 okay, and I will have also this one will be plus, and when I move it to the other side, it will be negative, right? Minus PV1, right? Minus with minus is positive. When I put it on the other side, it will be negative. Okay, then I can rearrange this one and say I have U2 plus V2 minus, I will take the minus as a common factor. It will be U1 plus PV1. Okay, so I will say that is H2 and that is H1. Okay, but the capital. So that is, you will find it a lot, this move in most of the questions of the business center. You need to put the boundary work in the other side and say I have delta H, because in the question you found he gave us what? He gave us CB. CB is always used with delta H. CV is used with delta U. So that is why I need to make this move. Okay. So I will have here delta H. Then I will replace delta H capital by delta H small, which is M, the mass times delta H small. Okay. So I will have I V delta T. I have all of this. I have Q out. Then I want to calculate H2 and H1. Okay. But I don't have the mass. I can get the mass because I have a lot of properties at state 1. I have the volume, I have the pressure, I have the temperature. So I will not face the same problems that I faced when I use the ideal gas law for the second state. So I can use the equation for the ideal gas law for the first state will be B1 equal to mRT1. Then I can use this equation to calculate M. It will be B1 V1 over RT1. I have the pressure, it is 300 kilopascal. Okay. And the volume is 1. R is 0.297. And T1, you have to put it in Kelvin. Do not forget to put it in Kelvin. So it will be 45 plus 273. Then you can get the mass. The value of the mass will be 3.1764 kilogram. Okay. The temperature at the 300 kilopascal, the first temperature. Okay. Then I will replace delta H by CB delta T. Okay. You know that delta H small is equal to CB delta T. Okay. So I will replace it T2 minus T1. So I will have I V delta T again minus Q out equal to M CB T2 minus T1. Plus I have everything. I have T1, I have CV, I have the mass, I have Q out, I have everything. Then I can calculate T2. Shift solve with the calculator. Then you will find T2. You can put T1 here as in Kelvin or in Celsius. If you put it in Celsius, you will get the results of the temperature T2 in Celsius. If you put it in Kelvin, you will get it in Kelvin. So it is in Kelvin 360.72 Kelvin or in degrees Celsius, it is 87.72 degrees Celsius. So that this question was a previous quiz for chapter 4. Okay, the previous 2 semesters. Do you have any questions regarding this problem? Because delta H capital, this one is in kilojoule. Okay, and this one is in kilojoule per kilogram. You will just put it on in terms of the mass. Okay, so this one is in kilogram, the mass is in kilogram, so that is the relation between them. Okay. Any other questions? Okay, help. Let's move to the next question. This one also has electrical heater. So I tried to get different idea from the YouTube tutorial, and I think this will be enough. I don't think that the doctor will bring something, a question that contains spring or something like this. I don't think so. Okay, usually he brings piston cylinder, unless he changes. Let's see. Uninsulated. What we mean by insulated, that we have insulation here that will restrict any heat transfer in or out. In the previous question, we had this 3 kilojoule that crossed the boundary out. Okay, but here we will not have any heat transfer in or out. Okay, whenever you see the word insulation installed, insulated, that means there is no heat transfer. Okay, no heat transfer, no Q. The cylinder device initially contains 1.8 kilograms, so that is the mass. The mass is 1.8 kilogram. Saturated liquid, we will use any property at HF, UF, the subscript F. Okay, saturated liquid at 120 degrees Celsius, that is T1 is equal to 120 degrees Celsius. Now, an electric resistor placed in the tank, similar to the previous one, is turned on also for 10 minutes. So delta T will equal to 600 seconds as the previous question. Okay, until the volume quadruples. That means it is 4 times the initial volume. So I have information that V2 is equal 4 times V1. Okay. Determine the volume of the tank. So in this question, in part A, he didn't decide, he didn't clarify which volume V1 or V2. Okay, so calculate both. Because sometimes in the questions in the midterm quiz, sometimes the doctor breaks something like this. دبر نفسك V1 or V2, calculate both. Okay, I think he will ask you to calculate the change in the volume in the question. Okay, so we need to calculate V1 and V2. I have the mass, and the substance that I have in this question is water. And we know water or refrigerant, we will use the tables. Okay, so I need to use the tables anyway. Okay, I have the mass. How to relate the mass to the volume? I need to calculate the specific volume. Okay, and say that the volume is equal to mass times the specific volume. This one is in meter cubed per kilogram, and this one is in kilogram. Okay, I have information that it is saturated liquid and it is at temperature 120 degrees Celsius. So I will go to the table at specific volume VF. Okay, I will go to the table that is water 120 degrees Celsius, which is here. Okay, and that is VF. That is the value of VF 0.001,060. Okay, so I will get the specific volume. V1 is equal to VF. It is 0.001060 meter cubed per kilogram. Okay. Then, in order to calculate the volume, I will multiply by the mass. So V1 is equal to MV1, and it is equal to 1.8 times 0.00106. which will give you 1.908 times 10 to the power negative 3 meter cubed. Okay, and thus I can know V2, right? V2 is equal to 4 times V1. So you finish part A, whether he asked for V1 or V2. So this will give you 7.632 times 10 to the power negative 3 meter cubed. Okay, let's see the second part B. Part B, he asked also for the final temperature. So in order to get anything from the tables for refrigerant or steam water, I have to have more than one property. Okay. يعني for our two informations in the previous state one I had two informations. It is saturated liquid and it is I have T1. So I directly went to the table and took the number. But here I don't have any information at all about state 2. Okay. Yani there is nothing mentioned about state 2, the temperature, the pressure, nothing is mentioned. Even the phase, is it saturated mixture, liquid, I don't know. So whenever you see something like this, يعني, do not panic. It is easy, inshallah. We know that we need to use the table. Okay, for state 2, what I can get for state 2 from the tables? I can get specific volume, right? Because specific volume V2, I already have the volume at state 2 and I have the mass. The mass will not change, either for state 1 or state 2. That's closed system chapter. Okay, the mass will not change. Okay, so specific volume V2 is equal to V2 capital over M. I have V2 is 7.632 times 10 to the power negative 3. And the mass is what? The mass is 1.8. Then specific volume for state 2 is equal to 0.00421 meter cubed per kilogram. So now I have one state. Okay, I have one property at state 2. I need another information. Okay, this information you will not find it unless you try to think about the question. Okay, I have saturated liquid. I got electrical heater. The electrical heater will increase the temperature of the saturated liquid. So it will increase the temperature until what? Until it is still saturated liquid? Of course, no. It will be maybe it is saturated mixture. Maybe it will reach saturated vapor. Maybe it will reach superheated. So I need to check. I have the value of the specific volume. I will go to the table at the saturation temperature, which is 120 degrees Celsius, because it is saturated liquid, right? The saturation temperature is something like this. That is T sat, which is equal to 120 degrees Celsius. It is T1. I have here saturated liquid. Okay. I have the mixture in between. I have here the saturated vapor. So it is the same temperature for all of them. Okay. I need to check the specific volume, the value of specific volume. Did it exceed the saturated vapor until superheated, or it is still in the mixture region? Okay. So I'll go to the table. The value of VG is 0.89133. So the value that I had is less. It is 0.00421. So I am in the mixture region. So T2 is equal to T1. It is equal to the T sat. So that is the solution for the second part B. Okay, so T2 is still equal to 120 degrees Celsius. That means also that the pressure is the same. The pressure is constant. Okay, so B1 is equal to B2, and this question also is quasi-equilibrium process. Okay, because the pressure will be corresponding to the saturation temperature. So the pressure B1 and B2 is equal to 198.67. Okay. So I have T2. The remaining is to calculate part 3. Part C, he said calculate the electrical power rating. The previous question, we used the work, which is WEN. Here we want the power, so W dot. Okay, so W dot, it is equal, we say it is the same from physics 2. You call it B, which is IV. And it is also the work over the delta T, or the change in time. So it is also equal to the work En over the change in time. Okay, so the result will be in kilowatt. Okay, in order to get WEN, the work, of course, I need to use the energy balance. Delta T, I have it 600 second. So I need to get WEN from the energy balance. So also I need to do energy balance. So this is question for chapter 4. You need to do energy balance. Okay, so let's do energy balance. If I made energy balance, I will have WEN. Okay, Then also I will have boundary work because the volume increase, right? The volume in the second state is 4 times the volume at the initial state. So I will have boundary work out. Okay, I will put it out. So I will have boundary work out, and it is equal to I don't have kinetic energy change. I don't have potential energy change. So the remaining is delta U. Okay. Then I will move the boundary work to the other side and say I have constant pressure. So the only change is in volume. Then I will replace the change in internal energy with the boundary work with delta H. So I will have delta En is equal to delta H capital. Then it is equal to, I have the mass this time, and no need to replace with Cp delta T because that is for the ideal gas or for the gases only. Here I have saturated liquid, so I can bring the values from the table, H2 and H1 from the table. So I have this one, H2 minus H1. I have information about H1. It is H1 is equal to HF, right? Because he said in the beginning of the question, it is saturated liquid, right? As I calculated V1 equal to Vf, I will say H1 equal to HF. For H2, now we know it is mixture. Whenever you have mixture, you need to find the quality. That is a must. Any mixture state, you need to find the quality. Okay, so H1 equal to HF. Let's get it from the table. At the temperature 120 degrees Celsius. So HF is 503.81. Okay, 503.81 kilojoule per kilogram. Okay. H2, I need to get it from this equation. H2 is equal to HF plus X HFG. But I don't have X, so I need to use other property to find X. The other property that I have is V2. Okay, so V2 is equal to, let's put it in terms of the quality. I want to calculate the quality itself. So it will be V2 minus Vf. You don't have VFG for in the table for the specific volume, so you will put VG minus VF. Okay. So I will calculate right now the quality. So X V2, I have it. It is 0.00421. Okay. VF is the same as V1. It is 0.00106. Okay. 0.00106. VG is this value, 0.89133. Okay, minus VF again. So the quality will be equal to X2 will equal to 3.538 times 10 to the power negative 3. Then I will use this value in order to calculate H2. I will get HF is 503.81 plus X2, which is 3.538 times 10 to the power negative 3. And HFG is from the table at the 120 degrees Celsius temperature, 2002.1. Okay, so H2 will equal to 511.6 kilojoule per kilogram. Now I will replace the values of H2 and H1 in the equation of the energy balance in order to calculate WEN. Then I will divide WEN by the time change, delta T 600 seconds, in order to get the power. Okay, so W, the work in kilojoule, is equal to 1.8 times 511.6 minus 503.81. I will get the value to be 14.022 kilojoule. Then I will divide this value by the time in order to get the power. It will be WEN over delta T. And this will give you 14.16 over 600 second, and this will give you at the end 0.02337 kilowatt. Okay, that is for the second question related to chapter 4. Any questions? Can you repeat why was T2 equal to T1? In part B, you found first that the specific volume, you found a specific volume at state 2, right? It is 0.00421. When I go to the table, 0.00421 is between these two values, between 0.00106 and 0.89133. So it is saturated mixture. So the temperature will remain the same. Okay, the temperature change only when you have a change in the phase. يعني, you will be in the superheated. But saturated liquid, so saturated mixture and saturated vapor has the same temperature always. Okay, so that is for this question. I think that is enough for chapter 4. Because we need to solve on chapter 2 and 3. Do you want to break 5 minutes or نكمل ولا ايه؟ ها؟ ايه تعال طب يلا. I think this question maybe Loden solve it with you, but I will solve it again because it already came before in one of the midterms. Okay, from 2 years ago, and this the other question about chapter 2. This question also came in the previous semester, or previous semester, or the semester before the previous one. Okay, so usually in the midterm for chapter 2, you will have question related to efficiencies. Okay, the efficiencies of the turbine generators, turbine generator, or the efficiency of the pump and motor. Okay, so here in this question, he said that we have water in a large lake. Okay. Large lake like this one, large lake, like the one used in the dams, you can assume it is a river. Okay, that is a large lake. Why he want to mention that I have large lake, and why he mentions this specifically, that you need to think about the water in this large lake. First thing that the water is not moving. يعني relatively the water of this lake is not moving or stationary, so I can say that the kinetic energy is equal to 0, okay, because the velocity is equal to 0, okay, and also because now I will talk about the mechanical energy, because if you continue the sentence, he will say is to be used to generate electricity. So how the water in the large lake is used to generate electricity by the installation of a hydraulic turbine generator at a location where the depth of the water is 50 meters. Okay, so at this, I need to understand what is the purpose of having a hydraulic turbine generator. Okay, and whenever I understood this, the purpose of hydraulic turbine generator and how it will convert the potential energy of the water to be electricity, I can solve the question. Okay, so I have, let's look at the water now. The kinetic energy is 0, and the flow work B over rho is 0, because when we talk about the mechanical energy of a flowing fluid, we say that I have kinetic energy V squared over 2, and I have the potential energy, and also I have the flow work. Okay, it is not moving, so the kinetic energy is 0. The flow work, the meaning of flow work, that there is a force of the or a force caused by a pressure to move the water or any substance a distance, okay, a specific distance. So if I have an area and I have a pressure and the water will move inside the pipe, I will have flow work because I have this area and I will move a distance d. Then I will have area times distance is volume, and the one causing this work is the pressure. So I have BV, the flow energy or the flow work. Okay, because the same as what we did in the boundary work. I will do it again. Okay, I will say that any work is equal to force times distance, and the distance, the force here is pressure times the area, and the distance will remain the same. So I will have BV. So that is the flow work. Here I don't have pressure that will move the water. The water is not moving. So also I can say that the flow work is equal to 0. Okay. Only that I have the things that I have is atmospheric pressure, which is not doing anything. Okay, so I have a potential energy for this water, because he said that in order to calculate the potential energy, I need to put a reference. We will put a reference at the bottom or the lower level of the lake. Okay, usually when you have a dam set, okay, and you have here the lake, and then it will be at the elevation or elevation under the previous location, okay, with a distance. Okay, and this distance is 50 meters. So if I talk about the lake at the state 2, for example here, so I can say that Z2 equal to 0. I will take the datum or the reference here, and Z1 here is 50 meters. Okay, so I don't have for the lake at the second state anything. I don't have potential energy. It is also not moving, so the kinetic energy for state 2 is equal to 0, and also the flow work is equal to 0. Okay, the flow work 1 over rho is equal to specific volume, so it is the same. Either I say BV or pressure over density. Okay, why I'm doing all of this? Because I need to calculate the change in mechanical energy. Why I care about the change in mechanical energy? This is related to the role of having a hydraulic turbine generator. So that is the real turbine in real world. It will have an inlet, okay, and it will have an exit. So the water will move from the dam or from the lake through the inlet of the turbine and will go out in the other pipe. Okay, what is happening inside? That you will have blades or shafrot. Okay, when let's forget about these photos. Okay, I have here the water is coming from the lake. Okay, or from the I have pipes that are from connected to the lake, and the water will come until it reaches the inlet of the turbine. Okay, then it will exit from the outlet. I have here blades. Okay, the blades when the water strikes the blades will rotate. Okay, when it rotates, the turbine itself is connected with a shaft. Okay, this shaft is connected to a generator. Okay, when the blades rotate, it will rotate the shaft with it. Okay, and will rotate something called a rotor in the generator, which will create magnetic field, and by induction, it will produce electricity through the power lines. Okay, so why or the purpose of having a turbine, that when the water strikes the blades, it will convert its mechanical energy to the blades, okay, and then its mechanical energy will reduce. Okay, so at the beginning it has only the potential energy, Gz. Okay, we say the kinetic energy is 0, the potential, the flow work is 0. Only the only thing that I have is the potential energy, and at the end I have nothing. Okay, everything is 0. Okay, so that is why there is a reduce in the mechanical energy. Why I have value in the beginning, I don't have value at the end, because some of the mechanical energy is converted to the shaft when the water strikes the blades. So the blades absorb the mechanical energy. Some of the energy also, of course, is released as heat or due to friction. So here you have a mechanical energy, and it's the mechanical energy, the potential energy will start to decrease, and the kinetic energy will increase because the water is flowing. So velocity is increasing until you reach here where you have 0 potential energy. Okay, so that is the purpose of having a hydraulic turbine generator. The role of the turbine is to reduce the mechanical energy and convert it to a shaft work, and this shaft work will be an input to the generator that will produce electricity. Okay, so if you think about the efficiency, it is always the desired output over the required input. So the desired output of the turbine is what? Is to produce shaft work to the generator. So what is the required? What is the something that I lose? Is that I am reducing the mechanical energy, reducing the potential energy from the initial state to the final state. So if you see the efficiency of the turbine, it is work shaft out. That is the thing that I like, that I want. And what I am decreasing is the mechanical energy of the fluid itself. So it is the decrease of mechanical energy that is the one that I am consuming. For the generator, it is the opposite. The shaft work out from the turbine is a shaft work in for the generator. It is the same shaft work, but it is for the turbine, it is out, for the generator, it's in. So I am consuming for the generator the work shaft in, and I'm producing electricity. Okay, so in this question, if you have any question, interrupt me at any time. Okay. Water is to be supplied at a rate of 5,000 kilogram per second. So I have the mass flow rate that the water is moving with is 5,000 kilogram per second. Okay. If the electrical power generated is measured to be 1,862 kilowatt, electric power is generated by what? Generator, the last thing that I have. Okay. So I have the electrical power, W dot electric out, I have it. And I have the efficiency of the generator itself. Okay. That means if it is 95%, that 95% of the shaft work is converted to electrical work. Okay. I have only loss of 5%, which is very high. Okay, the first question or the first part is asking about the overall efficiency. The overall efficiency, the meaning of the overall efficiency is multiplying the efficiency of the turbine by the efficiency of the generator. Okay, so it will result at the end to be W dot for electrical out, which is the last thing that I have that I will be produce. And the first thing that I consumed is what? The mechanical energy decrease due to turbine. Okay. So if you put the two equations, this one and multiplied by this one, you will find that you are canceling work shaft in by work shaft out, because it is the same. Work shaft in from the to the generator is the same as the work shaft out from the turbine. So I will cancel this by this, and the remaining is W dot electrical out and the delta E mechanical decreasing in the denominator. Okay, so then I can calculate the overall efficiency. So I have for the overall efficiency, the W electrical out, I have it. It is given in the question. Okay, I need to calculate delta E mechanical, and we said that delta E mechanical, I only have GZ1 is the only thing that I have, because the kinetic energy for both state 1 and state 2 at the upper leg or the bottom of leg, it is not moving, so kinetic energy is 0. I put the potential energy for the second one is 0 because there is no height. I take it already. It is my reference. Okay, and the flow work, we say the flow work, we need to move or put a force to move the fluid. Now the fluid is not moving, so it is also 0. And even if you assumed I have flow work, both of them has the atmospheric pressure, you will cancel both of them. Okay, so this one will be the delta E mechanical decrease. Okay, so I have 9.81, the gravitational acceleration, and Z1 is 50. But this result will be, this one is meter per second square, and this one is meter. This will be meter squared per meter square per second square. You have to convert it because we usually deal with kilojoule per second or kilowatt, and I already have the electrical power is in kilowatt. So I need to use a conversion factor, which is like 1 kilojoule per kilogram is equal to 1,000 meter squared over second squared. So we need to divide by 1,000, okay, in order to cancel the meter squared per second square and have the value in kilojoule per kilogram. So the value will equal to 0.491 kilojoule per kilogram. That is the decrease in mechanical energy. Then you can find directly the value if you substitute it here and with the electrical out electrical work out given, you will find the overall efficiency. This is the overall efficiency. Okay, it will be equal to 1,862 over 0.95. No, that is not the overall efficiency. I have it. Here I will put 0.491. Okay, the results will be حد معاه كالكوليتر؟ نعم 3000 متأكد. انا حاسس مش فاكر الرقم ده. 92 اشوف السوشيال مان ولا اسهل. اتفضل تمشي. اصل المهم يعني انها هي ديت. Okay, it is equal to 0.7. Because sorry, we forgot to multiply by the mass flow rate. We have a mass flow rate 5,000 kilogram per second. Okay, so if we multiply by the mass flow rate, you need to multiply first. Okay, so it will give you أيوة فين 0.74. Okay, so that is the overall efficiency. Okay, then for the second part B, you need to calculate the mechanical efficiency of the turbine. The mechanical efficiency of the turbine, I need to find, I have the W mechanical fluid. Already I calculated the W mechanical fluid, and I don't have the work shaft out, right? The work shaft out, I can get it from the third equation, or the third equation here for the generator, because I have the efficiency, and I have the W electrical out given in the question. I get the work shaft in. Then I return back to this equation and get the work shaft in, and I already calculated the mechanical decrease and the mechanical energy decrease of the fluid. Then I will get the mechanical efficiency of the turbine. Okay? Is it clear or no? يعني بس خلاص أنا نفسي تعبت أصلا. Okay? So that is for this question. Nothing to be added. Let's move to the pump. Okay. You have also three equations. The one for the efficiency of the motor, the efficiency of the pump, and also you have the overall efficiency. Okay. Always in the question, if you don't need to any headache to understand, you'll have always two givens that you can use in order to find something. Then you can use the other equation. Then you can use the other equation. Okay. Water is pumped from a lake to a storage tank. Here's the storage tank. 15 meter above at a rate of 70 liter per second. So I will assume this one is my reference. So I will give it Z1 equal to 0. I will assume this is Z2. I will give it 15 meter. Both of them is at the atmospheric pressure, and they are not moving. So the flow work for both of them is equal to 0. Okay. And also both of them are not moving. So the kinetic energy of the two states are also 0. So usually in this application, the only thing that you care about is the potential energy. Okay. In your quiz, when you have the wind turbine, okay, the air striking the turbine, it is a wind turbine. The application there is the kinetic energy. Okay. The important thing, that's why you use V squared over 2. Here, the most important thing is the potential energy. Even if there is kinetic energy flow work, the value or the amount of the flow work or the kinetic energy is very low compared to the potential energy. That is the main purpose of having this application. You will have it also in the thermal system design course, this the pump design, and similar to this question. Okay. This one, 70 liter is volume. So I have the volume flow rate is equal to 70 liter per second. Okay. So it is, if I want to convert from liter to meter cubed, I have to divide by 1,000. Okay. 1 meter cubed is equal to 1,000 liter. Okay. Then you will have 0.007, something like this, I think. Okay. While consuming 15.4 kilowatt of electrical power. So also in this one, it is, you are given the electrical power. The difference between pump and motor and the generator, hydraulic turbine generator, that the motor will come first. The motor will operate the pump. But in the turbine generator, the turbine is the one operating the generator. So here, what is happening, that the water will come, okay? And the electrical motor is connected to electricity, and it will cause a shaft work here. The shaft work will rotate some blades on the pump. These blades will increase the mechanical energy. Here, the role of the pump is increasing the mechanical energy. The role of the turbine is decreasing the mechanical energy. So the mechanical energy will be increased. So because the blades will strike the water and increase its pressure up. So here the delta B is important because you are increasing the pressure of the water. Okay. So the motor will come first. Okay, so I have the work shaft, the electrical power, disregarding any frictional losses in the pipe or any change in the kinetic energy. So you will assume that kinetic energy is very low. I will ignore it. The frictional loss of the friction between the fluid itself and the fluid and the pipe connecting the pump and the storage tank, they will ignore it. So determine the overall efficiency of the pump. Okay, so the overall efficiency of the pump has this equation. I have W electrical N, it is given. Calculate the delta E mechanical. The only thing that I have is the potential energy. Okay, so I will calculate it to be Z2, GZ2, and also do not forget to divide by 1000. So I will have 9.81 times 15 over 1000. Okay, and we made the same mistake. We forgot the mass flow rate. Here I have the volume flow rate. In order to get the mass flow rate, it is the mass flow rate is the density times the volume flow rate, right? Okay, so it is 1000. It is water. 1000 the density, and the volume flow rate is 0.07. We convert it, right? Yeah, I think. Okay. Then you get the mass flow rate, multiply the mass flow rate here. So we can put here also 1000. It will cancel with the 1000 that we bought. Okay, and multiply by 0.07. It is easier to look at the solution. That is question 268. Okay. He calculated the mass flow rate and calculated the potential energy. When you multiply them together, you will have the change in mechanical energy, the increase in the mechanical energy. Then you can find the overall efficiency. You already have the electrical power given in the question. You calculate the delta E mechanical fluid. Then the second part, he will ask about the pressure. Okay. Here's an important part. Change in mechanical energy. The work will be always يعني put it positive. Okay. Yeah, exactly. It must be positive. And if you notice in the equation for the turbine, they put the absolute value of the mechanical energy because it will be decreased. Right. Here he puts the absolute value because the decrease in mechanical energy will give you negative results. So always put it in positive. Okay. Here the second part, he will ask about the pressure difference because it is important for the pump. The pump, the purpose of having a pump is to increase the pressure. So I need a certain increase in the pressure in order to provide the water to reach the surface or the storage tank. If I have a lower pressure, maybe I cannot reach the storage tank. I cannot provide the storage tank. So I need to calculate the delta V, the pressure difference. Okay, when you calculate the pressure difference of the pump, you need to take the pump as the system. In the calculation of the mechanical energy, we assume that that is the first point at the lake, and the second point here at the storage tank. Now I am talking about the point in the inlet of the pump and the point at the outlet of the pump. Okay, so as I am taking the pump as my system, of course, there is no change in potential energy because the pump is a device. I cannot assume there is a difference between the inlet and the outlet. I will assume both of them equal to each other, or I will cancel them. So potential energy Z1 or Z2 for them is equal to 0. Okay. I'm talking this one is state 1, this one is state 2. The new state 1 is state 2. Okay. The kinetic energy, there is kinetic energy, but we will assume it is also small. There is a lot of assumption because usually the pump, will assume that the area is constant for the inlet and the outlet. Okay, so since the area of the inlet and the outlet are the same, if you know that the volume of fluid itself is the same, that means that the velocity is the same. So even if they are the same and they have kinetic energy, also we will say it is compared to the flow work. Okay, they are minimum. So that if I have V squared over 2, it is compared to the flow work, it is very small compared to the flow work. So I'll have only at the inlet and the outlet the flow work. So I will say that I have only flow work B1 over rho and I have only B2 over rho. Okay, that is the main contributor of the increase in the mechanical energy. So always the increase in the mechanical energy is related to pressure. In the turbine, it is related to the decrease in the pressure. In the turbine, it is related to the increase in the pressure. So I can say that change in mechanical energy is always equal to the change in the flow work. Okay, and this one was in dot, so we need to put the mass flow rate. So this one is V dot. So mass flow rate over rho is V dot. So that is the a question that came before in the exam, in the midterm exam. And also, if you are talking about the turbine, it will give you the same equation. Okay, but the delta B will be the negative. Okay. So the solution is here. Delta B is equal to delta mechanical. I already calculated delta ME mechanical. Okay, and the volume rate, I have it. I can get the change in the pressure. Okay, because if you see the book, chapter 2, you have something here. Here he said in this question, this W max. Okay, and he said the similar equations that we put in the previous when we solve. Why he put W max? If you ask about W max means that the efficiency is 100%. Okay, if the efficiency is 100%, that means that the W max, okay, or the W is equal to the mechanical of the energy change of the fluid. So the efficiency is 100. Okay, that means this one is equal to this one, and that is why he said W max. Okay, but this case you will not have it in the real world. Okay, so that is for this question. Try to understand how each of these systems are working. Still, we have one question. I will solve the question of the quiz chapter 3, the table, because usually it will come in the midterm. I have another tutorial in chapter 4. The beginning of chapter 4, the first 15 minutes, is a solution of the quiz 3 previous quiz. It is also a table. Okay. The first thing that you need to think about, read the question. It is R134A, not water. Okay, do not use the table for water because you know how to solve, but you use another table. Okay. So it is R134A. You will use table A11 to A13. Okay. Now I have the pressure. I go to table A12. I close the tables. Table A12, the pressure table. At 600 kilopascal. Okay, and let's see what we need to calculate. I have another value, which is the enthalpy. Let's see the enthalpy. It is 180. 180 is between the HF and HG. So the state that we have is a mixture state. Okay, so it is a saturated mixture. Okay, so whenever we say that whenever we have a saturated mixture, there is a must to calculate what the quality. Okay, you cannot directly get any value from the table without calculating the quality first. Okay, we need to calculate the quality. I can calculate the quality from where? From the property that I have, which is the enthalpy. So I can say that x1 is equal to h minus hf over hfg. Okay, and I get the values from the table. H, the one that I have is 180. HF is 81.51. HFG is 180.9. Then the quality is equal to 0.544. Okay, so why I calculated the quality? Because I will need it to calculate the internal energy. Any properties that at a saturated mixture state, you need to use the quality equation. So U1 will equal to UF plus X1 UFG. And I will use the tables. Okay, if you go to the table, you will find that UF is 38.4. X1 we calculated X1 to be 0.544, and UFG is 186.14. Then you can calculate U. You need to continue or يعني have a general idea about the quiz, because يعني it will be easy to solve this quiz. But another يعني thing that I want to mention, that for example this one is the row number 3. I have the pressure is 500 kilopascal and the temperature is -14. -14 15.71. So it is compressed liquid, right? Compressed liquid, in order to find any property of the compressed liquid, you need to use the temperature table, not the pressure table. So you made the assumption correctly that I will approximate the HF or UF, U or H to be UF or HF, because compressed liquid is approximate to saturated liquid, but at the temperature table. So instead of getting the value here, HF is equal to 73.33 at the pressure table, that is wrong. You need to go to the temperature table, okay, and find at the -14 degrees Celsius the value of the HF. So always when you make the assumption that the compressed liquid is saturated liquid, go to the temperature table, because it is mentioned in the book that I don't know where that the compressed liquid or the liquid itself is dependent on the temperature more than the pressure. They tried to increase the temperature 100 times. It will not. It didn't affect the property or the value of the property more than 1%. So always it is a function of temperature. So that is why you need to find a temperature table. Anyone has any question related to anything? Do you need me to continue the solution of this question? خلاص ايوه. Stop the recording. Send the recording. Okay, I will send the recording ان شاء الله. Here you will find that we'll say that T that I have, which is -14 degrees Celsius, is less than that saturation temperature, okay, which was 15.7 something, okay. That means it is compressed liquid, right? And I will assume that the compressed liquid is approximately a saturated liquid. If it is saturated liquid, so I will use any property with a subscript F, right? H. So here, if I want to calculate the enthalpy, so the enthalpy will be equal to HF at the temperature -14 degrees Celsius, not at the pressure 500. So use the temperature table, not the pressure table, okay? Because it is will give you different values. So the other are very easy يعني ان شاء الله. بس كده خلاص خلينا كفايه.
سؤال توقع حاكي بس كثير
يعني ممكن اسالك what is the name of the work of the turbine? Shaft work, like the previous question, chapter 2. What is the driving force of the heat transfer, temperature difference? All the theory from Dr. Steve is from the slides. ان شاء الله بتكون سهله يعني ان شاء الله. بس ما عملناش ريكوردنج بعد كل لا استنى، معمول الحمد لله. لان انا شرحت الكلام ده قبل كده برضه ما عملتش ريكوردنج، فيعني